Hello students, I hope you all are doing good. Today we will be discussing NCERT section 14.1 to 14.2 of chapter Semiconductor Electronics, Materials, Devices and Simple Circuits. This is the disclaimer. During competitive exam preparation, focus on understanding the classification of semiconductors, intrinsic, extrinsic, conductive types, and the basic concept of energy band theory. This will help you grasp how semiconductor materials behave under different conditions. Focus on learning key concepts like intrinsic and extrinsic semiconductors, doping effects, and their impact on conductivity. Focus on understanding PN junction formation behavior and how it operates under forward and reverse bias. Understand how a junction diode functions as a rectifier by grasping its forward and reverse bias behavior. Practice diode applications like rectification and voltage regulation. Learn applications in modern electronic devices and integrated circuits. Stay consistent, analyze mistakes, and maintain a balanced study schedule for effective exam preparation. Practice past year JEE and NEET problems from official sources, improving time management and regular revision. For further guidance and books, visit https://forum.pruter.ai. Let's start by looking at what you will be able to understand after this lecture. After this lecture, you will understand how electronics evolved from vacuum tubes to semiconductors, highlighting key historical milestones and the impact of this transition on modern technology. You will study how materials are classified as conductors, semiconductors, or insulators based on their energy bands, conductivity, and how temperature affects their electrical properties. In today's lecture, we will discuss the NCERT section 14.1, that is introduction part of this chapter. Then we will discuss the section 14.2, classification of metals, conductors and semiconductors. Evolution of vacuum tubes to electronic devices marked a shift from bulky, power-hungry components to compact, efficient semiconductors, enabling modern technology and miniaturization. Electronic circuits rely on devices that control electron flow. These devices, like transistors and diodes, manage electricity by allowing or restricting current. Before the 1948 invention of the transistor, electronic devices relied heavily on vacuum tubes, also known as valves. These components were used to amplify and switch electrical signals. Vacuum tubes were bulky, power-hungry, and prone to failure, limiting the size and efficiency of early computers and radios. A vacuum diode consists of two electrodes, the anode, also called the plate, and the cathode. It operates in a vacuum to prevent current flow in the reverse direction. A triode is a vacuum tube with three electrodes, the cathode, plate, and grid. The cathode emits electrons, the plate collects them, and grid control the flow of electrons between them. A tetrode has 4 electrodes, with the pentode has 5. Both are vacuum tubes used in amplification, with pentodes offering better performance due to their additional electrode. So we are continuing our discussion on the evolution of vacuum tubes to modern electronic devices. Let's briefly explore how these early components laid the foundation for today's technology. Vacuum tubes are electronic devices used before transistors. They consist of three main parts: the cathode, anode, and grid. The grid placed between them controls the electron flow by applying a voltage, thus regulating the tube's operation. In a vacuum tube, the heated cathode emits electrons through thermionic emissions. A vacuum tube is an old electronic device that controls electricity by using a vacuum inside a sealed glass or metal container. It contains electrodes that allow or block the flow of electric current. A vacuum tube uses thermionic emissions, where heat causes electrons to be released from a heated cathode. These electrons are then drawn toward a positively charged anode, creating an electric current. A vacuum tube consists of a control grid between the cathode and anode to manage electron flow. This grid controls how many electrons reach the anode, allowing the tube to amplify or switch electrical signals. Let's discuss the limitations of vacuum tubes. Vacuum tubes are bulky, making them hard to fit in small spaces. This limits their use in modern electronics, which require compact designs. High power consumption refers to using a large amount of electrical energy. Vacuum tubes consume high amount of power. High voltage operation, around 100 volts, refers to using higher electrical potential to power devices. Vacuum tubes operates on high voltage. Vacuum tubes had a limited life because their internal components like filament would wear out over time. This made them unreliable for long-term use. Vacuum tubes had a low reliability due to their fragile glass construction and susceptible to thermal stress. They often failed over time, leading to frequent replacements. The semiconductor revolution transformed electronics by replacing vacuum tubes with solid state devices. So you can see in the diagram. So figure evolution from vacuum tubes to semiconductor devices showing size, power and efficiency improvement. You can see that vacuum tubes are large in size and semiconductor materials are very small, relatively small in size than vacuum tubes. So modern transistors differ from old vacuum tubes by not requiring electrons to travel through a vacuum. Vacuum tubes used heated filament to emit electrons, which then moved through the vacuum to control current. Semiconductors work without needing extra heat or a vacuum, making them efficient and simple to use. Unlike some materials that require special conditions to function, semiconductors operate under normal conditions. This ease of use and high efficiency make them essential in modern electronics such as computers and smartphones. These semiconducting devices are small and use little power, making them easy to carry and energy efficient. Their compact design and size allows for portability, while low power consumption extends battery life and reduces energy costs. Semiconducting devices operate on relatively low voltage. Low voltage operation means using electrical system with voltages below standard levels like 12 volt or 24 volt. It also minimizes risk of electric shock and fire. Vacuum tubes enable early electronic devices by controlling electric current, but they had short lifespans due to heating and wear. Their evolution led to transistors and semiconductors, which are smaller, more durable, and provide longer life, making modern electronics reliable and efficient. Semiconductor devices provide high reliability. So cathode ray tubes monitors, CRT monitors, which use electron beams to display images are being replaced by LCD screens, liquid crystal display. So LCDs use liquid crystals and solid state electronics, making them lighter, more energy efficient, and less prone to flicker. This shift reflects advancement in display technology, offering clearer images and better performance. The replacement of vacuum tube devices like cathode ray tubes marks a shift from old technology to more efficient system. CRTs used in early TVs and monitors relied on vacuum tubes to display images by firing electrons at a screen. LCDs or liquid crystal displays have replaced older display technologies. They use solid state semiconductor technology, making them more reliable and energy efficient. Unlike earlier displays that used moving parts, LCDs rely on liquid crystals to control light, allowing for thinner, lighter, and more durable screens. Now we will study some historical context. Let's see some early applications of semiconducting devices. So before semiconductors were understood, scientists used a natural mineral called galena lead sulfide as a detector for radio waves. This was one of the earliest applications in radio technology. Galena, when touched by a metal contact, would detect and convert radio signals into electrical signals. This process, known as the galena crystal detector, was a key component in early radio receivers. It allowed people to listen to radio broadcast long before modern electronic components were developed. Let's begin by discussing how resistivity can be used to understand the behavior of materials. Resistivity is a fundamental property that determines how well a material conducts electricity, and it can provide insights into the material's atomic structure and electronic properties. So resistivity is a material's inherent property that shows how well it resists electrical current. It depends on the material and temperature, not on the object size or shape. It helps determine how easily electricity flows through different substances. Materials with high resistivity are poor conductors, meaning they resist the flow of electric current. In contrast, materials with low resistivity allow electric current to pass through easily. Conductivity measures how well a material allows energy like electricity or heat to pass through it. Materials with high conductivity such as metals let energy flow easily, while insulators like wood or rubber resist this flow. So based on electrical conductivity or resistivity, so electrical conductivity is represented by sigma, and it is exactly reciprocal of resistivity, or we can say resistivity rho is exactly reciprocal of conductivity. So solids are classified into metals, semiconductors, and insulators. So metals are excellent conductors of electricity due to their very low resistivity. Resistivity of metals ranges from 10 to the power minus 2 to 10 to the power minus 8 ohm meter. This means they allow electric current to flow easily through them, making them ideal for use in wiring and electrical devices. Electrical conductivity of metal measured in Siemens per meter ranges from 10 to the power 2 to 10 to the power 8 Siemens per meter, indicating materials can have varying abilities to conduct electricity. Semiconductors are materials with electrical conductivity between that of conductors like metals and insulators. Their resistivity ranges from 10 to the power minus 5 to 10 to the power 6 ohm meter. This unique property allows them to control electric current, making them essential in electronic devices. Electrical conductivity of semiconductors measured in Siemens per meter ranges from 10 to the power 5 to 10 to the power minus 6 Siemens per meter. Okay, Siemens is ohm inverse, indicating materials can vary from highly conductive like metals to very insulating like rubber or glass. Insulators are materials that resist the flow of electric current due to their high resistivity. They have very low conductivity, meaning electrons don't move easily through them. The resistivity of insulator ranges from 10 to the power 11 to 10 to the power 19 ohm meter, making them poor conductors. This property makes insulator useful for preventing electric shocks and protecting circuits. Electrical conductivity for semiconductor materials measured in Siemens per meter ranges from 10 to the power minus 11 to 10 to the power minus 19 Siemens per meter, indicating very low conductivity typically of insulators or very pure semiconductors. Resistivity measures how well a material resists electric current, but it's not the only factor in classifying materials. Metals, insulators, and semiconductors differ not just by their resistivity values but also by their atomic structure and how electrons behave. So, energy band theory explains how electrons behave in solids. It shows that electrons occupy energy bands, with conductors having overlapping bands, insulators having a large gap, and semiconductors having a small gap. This helps explain electrical conductivity in materials. Materials are categorized by how well they conduct electricity and their energy band structure. Energy band theory explains how electrons behave in solids. In metals, the valence and conduction band overlap, allowing free electron movement, making them good conductor. In an isolated atom, electrons can have only specific fixed energy levels. These are called discrete energy values, meaning electrons don't exist between these levels but jump between them. In a solid material, when atoms come close together, their atomic orbital overlap, creating a range of closely spaced energy levels. This range is called an energy band. Energy bands form the basis for understanding how electrons behave in solids, determining whether a material is conductor, insulator, or semiconductor. The overlap of orbitals lead to the formation of these bands, which are crucial for explaining electrical properties in materials. When atoms are far apart, each electron occupies distinct energy levels, such as 1s or 2s. However, as atoms come close to form a solid, their atomic orbitals overlap. This overlap allows electrons to move between atoms, creating new energy levels. These levels are no longer discrete but form bands, specifically the valence band and the conduction band. In solids like silicon, individual atomic energy levels such as 1s and 2s come very close together when atoms bond. This closeness leads to formation of energy bands, continuous ranges of energy levels. As atoms come close together, the space between them reduces, causing their electron energy levels to overlap. This overlapping leads to the formation of continuous energy bands instead of distinct energy levels. The valence band is the energy band that contains the energy levels of the valence electrons in an atom. Valence electrons are the outermost electrons involved in chemical bonding. This band determines how atoms interact with each other and influences the electrical and thermal properties of materials. The valence band is the highest energy level where electrons are tightly bound to atoms in a solid material. These electrons are not free to move and are involved in forming chemical bonds. In a solid material, the energy band above the valence band is called the conduction band. This band allows electrons to move freely, enabling electrical conductivity. In a material with no external energy, all valence electrons occupy the valence band. The valence band is the highest energy level where electrons are normally found in atoms. Without extra energy, electrons cannot move to higher energy bands, so they stay in the valence band. The conduction band is a range of energy levels in a material where electrons can move freely, allowing electrical conductivity. In solids, the conduction band is usually empty because electrons are in the valence band bonded to atoms. This means the materials doesn't conduct electricity. When the conduction band overlaps with the valence band, electrons can move freely between them. This allows for easy movement of charge carriers, which is why materials with this overlap, like metals, conduct electricity well. This is the case with metallic conductors. In metallic conductors, electricity flow easily due to free electrons that move throughout the material. These electrons are not tightly bound to individual atoms, allowing them to carry electric current efficiently when a voltage is applied. This property makes the metals excellent conductors of electricity. A band gap is the energy difference between the valence band and conduction band in a material. It determines how easily electrons can move between these bands, influencing electrical conductivity. An insulator has a large gap between its valence and conduction band. Electrons stay tightly bound in the valence band and cannot move freely to the conduction band. When materials have tightly packed atoms or molecules, electrons can't move freely, making the material an insulator. The Fermi level is the highest energy level occupied by electrons at absolute zero temperature, 0 Kelvin. At this temperature, all energy levels up to the Fermi level are filled, while levels above remain empty. At absolute zero temperature, the Fermi level is positioned exactly between the valence and the conduction bands in an intrinsic semiconductor. This means that all the energy states below the Fermi level are filled with electrons while those above are empty. The Fermi level acts as a reference point for electron energy levels, determining the material's electrical properties. At absolute zero, all electrons occupy the lowest possible energy level called the ground state. This happens because there's no thermal energy left to excite them. Without any energy input, electrons can't move to higher energy levels. The Fermi level is like the highest energy level that electrons can occupy at absolute zero temperature. It represents the boundary between filled and empty energy states. In a material, electrons fill all energy levels up to the Fermi level. The Fermi level is the energy level at which electrons occupy states at absolute zero. In solids, it shifts with temperature and electron concentration. When a solid is warmed, thermal energy increases electron movement, raising the Fermi level. Adding electrons increases the Fermi level, while removing them lowers it. Let us consider what happens in the case of silicon and germanium crystal containing n number of atoms. Silicon has its outermost electrons in the third energy level n equal to 3, while germanium has its outermost electrons in the fourth energy level n equal to 4. This means silicon is in period of 3 of periodic table and germanium is in period 4. In the outermost energy levels or valence shells, there are 4 electrons. These electrons are found in the 2s and 2p subshells. The 2s subshell holds 2 electrons and the 2p subshell holds 2 more, making a total of 4 valence electrons. This electron configuration is typically for arranged elements in the 14th group of the periodic table. such as carbon and silicon, and influences their chemical behavior and bonding capabilities. In a crystal structure, the total number of outer electrons can be determined by considering the contribution from each atom. For example, if each atom contributes 4 outer electrons and there are n atoms in the crystal, then the total number of outer electrons is 4 multiplied by n, or 4n. In the outermost energy level of an atom, the maximum number of electrons that can be held is 8. This is because the outermost shell can have up to 2 electrons in the s subshell and 6 electrons in the p subshell, totaling 8 electrons. In a 4n valence electron system, there are 8n available energy states. This means that for every valence electron, there are twice as many energy levels available to accommodate them. In a crystal, the atoms are arranged in a regular repeating pattern. Due to this arrangement, the energy levels of electrons, which are originally discrete in isolated atoms, start to overlap. When the atoms are close together, their energy level bends, forming continuous energy levels. However, if the atoms are spaced farther apart, the energy levels remain more distinct, leading to different bands. At absolute zero temperature, a semiconductor has its valence band completely filled with 4n electrons, as shown in figure 14.1. This valence band holds all the valence electrons of the atoms in the material. The conduction band located above it has a large number of closely spaced energy states but is initially empty. At 0 Kelvin, no electrons have enough energy to move to the conduction band, so the material does not conduct electricity. At absolute zero temperature, semiconductors have two main energy bands, the conduction band and the valence band. The conduction band is made up of a vast number of closely spaced energy states, but it's completely empty, meaning no electrons occupy these states. In semiconductors, the conduction band and the valence band are energy levels where electrons can move. The lowest energy level in the conduction band is called EC, and it's the minimum energy an electron needs to gain to move from the valence band to the conduction band, allowing it to the conduction electricity. The highest energy level in the valence band is the maximum energy an electron can have while still being bound to an atom. These energy levels determine how easily electron can move, which affects the material's conductivity. Above the conduction band, energy level EC, and below the conduction band, energy level EV. There are many closely spaced energy levels. These levels are part of the conduction and valence bands where electrons can move freely. At absolute zero temperature, the valence band in a semiconductor is filled with 4n valence electrons, meaning all the energy states are occupied. This band is the lower energy band. The energy band gap, or EG, is the energy difference between the top of the valence band and the bottom of a conduction band in a material. The band gap is energy difference between the valence band and conduction band in a material. This may be large, small, or zero depending upon the material. It determines how easily electrons can move, affecting conductivity. In this case, we are looking at the energy band structure of metals. The energy band diagram show how energy levels are arranged for electrons in a material. Metals conduct electricity because their electrons are free to move. This happens in two ways. First, in metals like copper or silver, the conduction band is partially filled and valence band is partially filled. This allows electron to move freely between the metals conductive. Okay, making the metal conductive. Second, in some metals, the conduction and valence band overlaps. When this happens, there's no energy gap between them. So electrons can move between bands without resistance. In a material, when the valence band and conduction band overlap, electrons can move freely between them without needing extra energy. This allows for easy movement of electrons, making the material a good conductor. When a material has a large number of free electrons in the conduction band, it becomes a good conductor of electricity. These electrons are not tightly bound to individual atoms or can move freely throughout the material. In a material, the valence band is where the outermost electrons reside. When this band is partially empty, meaning not all energy levels are filled, the electrons can move to higher energy levels within the band. This movement allows electron to gain energy and transition to the conduction band, where they can freely move and carry electric current. This process is essential for electrical conductivity in the material like conductors and semiconductors. In simple terms, resistance and band gap are closely related to how electrons move in material. Therefore, the resistance of such materials with partially filled valence band is low or the conductivity is high. Energy band theory explains how electrons behave in material. In metals, the valence and conduction bands overlap, allowing electrons to move freely, resulting in high conductivity and low resistance. Okay, and conductivity is of the order of around 10 to the power 8 Simon per meter. This means metals are excellent conductors of electricity. The diagram shows this band overlap, helping visualize why metal conduct electricity so well. Resistance in conductors increase with an increase in temperature. This happens because as temperature rises, the atoms in the conductor vibrate more rigorously. This vibration makes it harder for electrons to move through the material, increasing resistance. Examples: copper, aluminium, and silver are metals known for their excellent electrical conductivity. In case 2, we look at materials where a large energy band gap e.g. exists between the valence band and the conduction band. This band is greater than 3 electron volt, making it very difficult for electron to jump from valence band to conduction band at room temperature. In simple terms, an materials that has a large energy gap between its valence and conduction band more than 3 electron volt, this means electrons need a lot to jump from valence band to the conduction band. Since thermal energy isn't enough to provide this energy, electrons stay in the valence band and can't move freely. In a material where there are no electrons in the conduction band, electrical conduction is not possible. The conduction band is where electrons can move freely and carry electric current. If this band is empty, there are no free electrons to move under an electric field, so the material does not conduct electricity. This is the case of insulators. Insulators have a very large energy gap greater than 3 electron volt between their valence and conduction bands. Electrons cannot jump to the conduction band due to thermal energy limitations. Thus, no free electrons are available for electrical conduction, making insulators poor conductors of electricity. Insulators don't conduct electricity well with conductivity below 10 to the power minus 10 Simon per meter. This explains why materials like rubber or glass don't let electricity pass through them easily. The materials glass, rubber, and ceramics are examples of non-conductive substances. They do not allow electric current to pass through them easily. In case 3, the energy bands of insulators are shown in figure 14.2, third image. So a finite but small band gap, e.g. less than 3 electron volt, means there is a small energy difference between the valence and conduction bands. This allows electrons to gain enough energy from thermal or external sources to move into conduction band, unlike other insulators which have large band gaps. In semiconductors, a small energy gap less than 3 electron volt allows energy to jump from the valence band to the conduction band at room temperature, enabling electrical conductivity. This is why semiconductors conduct electricity but not as well as conductors. Energy band theory explains how electrons move in materials. In insulators, the energy band gaps are separated by a large gap. So electrons can't easily move, making the material non-conductive. In conductors, bands overlap, allowing free electron movement. Semiconductors have a smaller gap, enabling controlled conductivity due to the small number of thermally generated electrons. Semiconductors have lower resistance than insulators, meaning they allow some electric current to flow. Insulators strongly resist the flow of electricity, almost blocking it completely. Semiconductors are better conductors than insulators. Their conductivity is medium, between 10 to the power 4 to 10 to the power 4 Simon per meter. In semiconductors, as temperature increases, resistance decreases. This is because higher temperature provide more thermal energy, which frees more electrons from their atoms, increasing the number of charge carriers. With more electrons available to conduct electricity, the material's ability to conduct current improves, leading to lower resistance. Silicon and germanium are semiconductors with different band gaps. Silicon has a band gap of 1.1 electron volt, while germanium has a smaller band gap of 0.7 electron volt. This means electrons in silicon require more energy to move from valence band to the conduction band compared to the germanium. So let's summarize what we have discussed today so far. So vacuum tubes had limitations like high power consumption, large size and low reliability. Semiconductor revolution brought advantages like small size, low power consumption and high reliability. Detection of radio waves by galena crystal detectors was one of the first application of semiconductor technology. Semiconductors are the basic materials used in the present solid state electronic devices like diode, transistors, integrated circuits, etc. Lattice structure and the atomic structure of the constituent elements decide whether a particular material will be insulator, metal, or semiconductor. Metals have low resistivity, insulators have very high resistivity, and semiconductors have intermediate values of resistivity. Semiconductors are elements that is are elemental, that is silicon and germanium, that are pure semiconductor materials, as well as compound. Okay, so semiconductor materials can be made up of more than two elements. Okay, so it is gallium arsenide and cadmium sulfide. Energy bands consist of valence band and conduction band. Conductors have overlapping bands with high conductivity. So conductivity is of the order around 10 to the power 8 Simon per meter. Semiconductors have small band gaps, that is 0.123 electron volt, with medium conductivity of the order of the range 10 to the power 4 to 10 to the power 4 Simon per meter. Insulators have large band gaps greater than 3 electron volt with low conductivity, which is less than 10 to the power 10 Simon per meter. Resistance increase with increase in temperature in case of metals and decrease with increase in temperature in case of semiconductors. Common example of different type of materials, semiconductor materials are silicon, okay, that is semiconductor material, and other copper, that is conductor, and glass, that is insulator. Let's see some practice questions based on the topic that we have studied today. Draw the energy band diagram in case of conductors. What is Fermi level? What is the energy gap of silicon in electron volts? When temperature increases, does the resistance of semiconductor increase or decrease? And what is the approximate electrical conductivity range for semiconductors in Simon per meter? So this is all about today's lecture. I hope you enjoyed the session. Thank you for your attention.